Now, you have several case scenarios, and I recommend that you stop the video, and you can either take a snapshot, or you can actually draw this in your notes, however you wish to do. You have the first case is a fluctuating load. The fluctuating load doesn't necessarily start in zero. It just it doesn't it can look something like this as well. It's just fluctuating, right? It's fluctuating between a max and a minimum, and doesn't necessarily touch the zero or goes above the zero. In this particular case, your mean is right here, and the range and RA are given by this value. Okay, so then the and you have several cases in fluctuating load, right? This is in tension. This is in tension. They're fluctuating in tension because it's positive. Then you may have this case that's fluctuating. This is in compression. Okay, this is in compression. So now the other case that this is very, very popular, that you're going to see this in the books all the time, and especially in the literature, we have what we call completely reversed. Why we got all the test data is mainly because of fully reversed. Why? It's easy to model. I can take a testing, and I can say about my zero stress just go up and down, up and down, up and down, and I can follow this cycling mode. And if this was the case, then your maximum is equal to sigma sub zero. If this is your sigma max and sigma minimum, and sigma minimum is minus sigma sub zero, as you can see, then your mean stress is equal to zero. This is important, right? Anytime your mean stress is zero, typically refers to completely reversed case. And then you have this this ratios right here are typical of a fully reversed case. Okay, then you have another case in which it's repeated intention. Repeated intention, you can think when you sit on the bicycle, you get off the bicycle. You sit on the bicycle, you get off the bicycle. So you have you start with certain stress, and you go up, then you get off the bicycle. Now you have no stresses. You apply the stresses again, and then you have zero stresses. This is zero. Goes from zero to bottom, zero to bottom. And then the same thing here, it goes to zero, and it keeps on fluctuating from zero to a known value. Okay, so those are the various cases that we have. Now, to understand how we're going to analyze this, how we work these problems, I needed to look at the broader spectrum of the problems that we're going to solve. The first thing that we solve is, so in this case, when you do testing, typically most of the testing, and it's very common that we do it for the case of pure axial, pure bending. We can also do this for pure torsion. Okay, if it's only one case scenario, one loading, then it typically is done for a fully reversed, that your mean stress is zero, and this is what we call a category 1. This is very popular. We got the data for this testing, test data, and is well documented in many cases for many typical materials that we use, and we can use that. We have a second category in which now we can take this pure axial, pure bending, and pure torsion, which also we have data available for some material in some case scenarios. And this is fluctuating, right? Remember, when we say this is actually fully reversed. But here is fluctuating. It can look, it doesn't have to be above the zero axis. Now, the challenge here is, this is the challenge part. What we do here, this is where we got the challenge. There is not enough, we got some test data available, but not enough to know what happens in the multi-axial. So what happens when you have, in the case, you have an axial load, you have your torsion, you also have bending. Now what do? Now how do I go about this, right? So there are many different cases for ductile materials. There are different scenarios to work with brittle materials, and we will talk about those case scenarios. We talk what happens with fully reversed. We will talk when it's actually fluctuating. Okay, so this right here is going to depend on if we are working with ductile or if we are working with brittle. Okay. So before we move on any further and we keep on talking about these theories, let's understand a few things here. First of all, as I started our discussion, everything is talks about a crack growth. Okay, so it's nothing else than fracture mechanics, but fluctuating. When you fluctuate your load, then what's going to happen is your stress intensity factor is going to fluctuate, right? And then as you are fluctuating this, you can expect changes in your crack length because it's going to grow. So this scenario, this is very popular, this particular scenario. And what people do is to plot this. We got different cases for different type of materials. It's for steel, for different type of steels. And this is ferritic. This is because it has iron in it. And these are without iron in different cases. This is stainless steel. This is not stainless steel. This is done completely for R is equal to 0. So your mean, when this is almost equal to 0, you're saying that it actually your minimum is 0, right? So it's actually doing something like this. So you apply the load, you get off the load. You apply the load, you take off the load. That's what we're actually trying to do in this problem. For these cases, for different steels, this material data is available. And to understand how this actually works, you talk about region 1 is low speed propagation. So you don't have to apply very high frequency. But then as you're applying the load, it comes to a point where your crack becomes a little bit stable. So it's a stable crack growth, right? But then it comes to a point where it actually shoots up and breaks you apart. So our analysis typically is focused in this area right here. Okay, this is what we are trying to do. In region 1, the crack does not necessarily grow unless I start increasing my speed. Then in region 2, as I just explained to you, it stays constant and it stays stable. And region 3 basically fails. Okay, so this is the region 2 that's stable, and this is where we would like your crack to stay. Because it's there, it stays here. There's a way I can stop it from making it actually grow. Okay. So to better understand many of these topics, the question is, what do we do? How do we go about it? So I'm going to give you a strategy in which we're going to discuss what to do in the most general case for the multi-axial load. And then we do several cases in which we specialize it for strictly one case, strictly the other case, and we work around that. So if I had this case, first of all, the first thing you have to do in any problem, as we know, we want to multiply your design factor, right? So you're going to take your load N, M, and the torque. You can also do your V, and you multiply by your design factor. You multiply your design factor. And just remember that for our case, N was NXX, M here's MZZ, your torque was MXX, comes from your homework, and your V is equal to VY. Typically, we don't need your VY for nothing. This is not even used in the analysis. There's no test data available for it either, but just place it there for completeness. That's the first thing you want to do. Second thing you want to do is you want to understand how everything is working. right? You want to understand what NXX is doing. NXX can have is fluctuating loads, and then from here you will find your N mean, your N alternate. So you will just say, what is your N maximum plus N minimum, and you will divide this by 2, and you would take this N maximum minus N minimum, and you will divide by 2. So then you repeat the same problem again for your bending moment. You will say, let me put MZZ. And for your bending moment, again, you can have maybe a different loading sequence, but you will find your M, your alternate, your mean, and this is M max plus M minimum divided by 2. This is M minimum maximum minus M minimum divided by 2. Okay? Then you can also have your torque. And this torque, remember, these are the values that you get from your plots, from your shear moment diagram, load diagrams that we did in your homework 1 and 2. With that kind of about that load is that we actually do some fluctuation. Okay, so you have this, and now what you say, you can have a torque mean, a torque alternate, and that will equal to torque max minus torque minimum divided by 2. Torque max, I'm sorry, this is plus torque max minus torque minimum divided by 2. Okay, I am not going to include shear because shear plays no role. It's not necessary to calculate what really happens to shear. Okay, so to kind of understand what this is really doing and how this works, now from your loads, let's say NA and NM, you're going to calculate your stresses. Okay, you're going to calculate your sigma XXA is going to be nothing else than this divided by area. This is going to be nothing else than mean NM divided by A. This is if you have your moment, okay, moment alternate and your moment mean. This is going to be nothing else than your bending moment. Okay, this is your, so this is alternate, axial in mean. This is XX in bending. This is mean. This is alternate. And that would be your moment alternate divided by Z, your moment mean divided by Z. Then you can do the same thing for your torque. You got torque alternate, torque mean, and then from here I can find my tau XY in torque alternate, tau XZ, I'm sorry, tau XZ in torque mean. This is nothing else than this value, torque alternate divided by Q, torque mean divided by Q. Okay, so you have all your stresses now. So what you're going to do in the problem is you're going to take your problem, and now you're going to say, I'm going to build two stator stresses. One is alternate, sigma XXA, and you have to know what your critical location is. So you always have to start with your static analysis, okay? So let me write this down somewhere here. Okay, so right here, or let's do it right here. Let me finish this. Let me finish writing this, and then we will do sigma ZA plus sigma XX BA. This is alternate. This is tau XZ alternate. Okay, so I was just trying to say, before you do anything, you want to uh, do static first, find design point. Okay, the design point is either A or C. Typically, these are the two that we care for. So those are the two design points that you're looking for. This is the design point if M is present. Okay, if M was not present, for some weird reason this was 0, then it would be B or D. Okay, if M is equal to 0, there was no presence of a moment. Then from here, what you do is you find your principal stresses. Okay, so you have your sigma 1 alternate, sigma 2 alternate, and sigma 3 alternate. So you solve this, you find this your principal stresses. Then you solve exactly the same thing again for your mean stresses. Sigma xx mean plus in axial, sigma xx in bending in mean, 0, tau xz mean, this is 0, 0, 0, tau xz mean, 0, 0. And then from here, you're going to find your principal stresses that we're going to call the mean. These are the mean principal stresses. Okay. Now, they are different located. So what do we do now, right? Now I have this case, I have the alternate stresses. So you can basically see we are basically doing the problem over and over again, right? So now, before we did static, we just did one time and that was it. But now I have to do it for alternate. I have to do it again for the mean. And then what do I do next, right? Because I need to know one equivalent stress. We've got two cases, okay? So we have the case for ductile materials. For ductile materials, we have the case for brittle materials. Okay, there are two different approaches that we can use. Okay, in this case, the first approach we're going to use is we're going to use the von Mises. Okay, so for the von Mises, I can find sigma equivalent alternate, sigma equivalent mean. Okay, and then for my, this is von Mises, and then also what I could do is I could use principal stresses. So for the principal stress scenario, we just find sigma A, sigma 1m. So this part right here, this is what typically we do in the industry. It's very common to do this, but there are companies that actually do this as well. But this is common in the aerospace industry at least. In the brittle material, we got two ways we can go about this. The typical way that we do it is just go by 1A, 1M, and we just move on with that. The other way you could do it is just find your effective, if you remember your Mohr circle approach, effective alternate, you find your sigma effective mean, okay? So you could do either method, but in this course, we recommend you use this method, but this is what we typically do in the industry. And then for your homework and your assignment, you're actually going to evaluate compare this solution with this solution. We will do an example for that to better understand how this goes. So the big question that we have now is, there's one big question before we move on. The question is, what do we do in the stress concentration factors. Okay. What do we do for stress concentration factors? We will leave that topic for the next video. So one thing that you have to know is before you do anything, you need to solve this problem. Okay, you need to come to this point. Then you need to do the stress concentration factors. And then we apply the stress concentration factors. And then we're going to do the problem all over again. So I had to do them several times. So, and the stress concentration factor, that will be Kf instead of Kt. But how do we deal with that? What do we do? I'm going to discuss that in the next video. So this was a more of an introductory video, and this completes class number 8A for fatigue theory.